September 19th, 1941. A cramped office inside the McCord Radiator and Manufacturing Company plant in Detroit, Michigan. Frank J. McCord, the company's chief production engineer, stares at blueprints scattered across his desk while outside, the roar of industrial machinery fills the autumn air. He's been awake for 36 hours straight, his eyes bloodshot, his hands trembling slightly as he reaches for another cup of cold coffee. Before him lies a problem that has defeated every military contractor in America. The United States Army needs helmets, not hundreds, not thousands, millions of them. And they need them pressed from a single sheet of Hadfield manganese steel into a shape 7 inches deep with smooth, consistent walls that can stop shrapnel without cracking. Every military engineer McCord has consulted told him the same thing. Impossible. Steel that thick cannot be drawn that deep in a single stroke. The metal will split, the dies will shatter. You'll need multiple presses, multiple heating cycles, multiple forming stages. You'll be lucky to make 200 helmets a day. McCord picks up the Army's specifications one more time. Minimum 2¼ pounds per shell. 7 inches in depth from a flat disc of manganese steel. No welds, no seams except at the reinforcing rim. Delivered at a rate sufficient to equip America's expanding military before war arrives at American shores. The contract calls for over 320,000 helmets before Christmas. Just the first batch. He knows what's really being asked. Can American industry transform cold, rigid steel into protective shells faster than German U-boats can sink the cargo ships that will carry American soldiers to war? The mathematics are brutal. Traditional helmet manufacturing requires multiple forming operations. Heat the steel blank, press it into a shallow bowl, reheat, press deeper, trim, anneal. Each step takes time, specialized equipment, and skilled metal workers who don't exist in the numbers needed. The British are still making Brodie helmets using techniques from World War I, 3 separate forming operations per helmet. The Germans use similar multi-stage processes for their distinctive coal scuttle Stahlhelm. Everyone accepts this as the natural limitation of metalworking. You cannot force steel to flow like water. Physics simply doesn't allow it. But McCord Radiator had spent 23 years making automobile radiators, transforming flat sheets of copper and steel into complex 3-dimensional shapes at high volume. The company's engineers understood something that military contractors did not. The limitation wasn't the metal. It was the tooling. Conventional dies tried to force steel to conform instantly to the final shape, creating stress fractures and tears. What if instead you allowed the steel to flow gradually into position, controlling every stage of its transformation within a single continuous stroke? If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. McCord's proposal to the Army Ordnance Department had been considered nearly impossible. A single-stroke deep-draw press capable of transforming a flat disc 12 inches in diameter into a helmet shell 7 inches deep. The die design would need to control metal flow with mathematical precision, preventing wrinkles while avoiding the tearing that destroyed conventional deep-draw attempts. The press would require perfectly calibrated tonnage, neither so weak it failed to form the steel nor so strong it crushed the die. And it would need to do this hundreds of times per day, every day, for years. The Army had given McCord the contract anyway, not because they believed it would work, but because every alternative was worse. American industry in 1941 faced a crisis of capacity. The nation's military was expanding from a peacetime force of 240,000 to a wartime army of millions. Britain was crying out for equipment after Dunkirk. The Pacific looked increasingly dangerous as tensions with Japan escalated. America needed to arm itself faster than any nation in history had ever mobilized. There simply wasn't time for conventional manufacturing methods. McCord returns to his calculations one more time. The deep draw ratio, the relationship between the blank diameter and the punch diameter, couldn't exceed 2.2 to 1 without risking catastrophic failure. The steel grade specification called for Hadfield manganese with specific carbon content for maximum toughness without excessive brittleness. The die geometry required radiuses calculated to within thousandths of an inch. Too sharp and the steel would tear, too gradual and it would wrinkle. He's been refining these numbers for 8 months. The breakthrough had come from an unexpected source. One of McCord's tool designers, a man named Carl Reichert, who had learned die making during the Depression, suggested treating the helmet press like a radiator tank former. Instead of forcing the steel into shape all at once, design the die with progressive forming stages built into a single stroke. The blank would encounter a series of carefully calculated shoulders and radiuses as the punch descended, each one drawing the metal slightly deeper while maintaining uniform wall thickness. The steel would flow naturally into the final shape, redistributing its mass gradually rather than being shocked into submission. Building the dies had taken 6 months. Each die set cost more than a new house in Detroit and weighed several tons. The steel had to be heat-treated to precise hardness levels, neither so soft it would deform under the crushing forces of repeated stamping, nor so hard it would crack. The forming surfaces required polishing to near mirror smoothness. Any imperfection, any rough spot or tool mark, would telegraph through into every helmet pressed from that die, creating stress concentrations where shrapnel could penetrate. The press itself was a machine from another era, a massive mechanical beast powered by a flywheel the size of a dining room table. It had been built originally for pressing automotive body panels, but McCord's engineers had modified it extensively. New controls allowed the operator to adjust the stroke length and descent speed. A cushion system underneath the die provided resistance during the draw, keeping the blank holder tight against the steel to prevent wrinkling without crushing the metal. The whole assembly stood 3 stories tall and shook the factory floor with every stroke. June 26, 1941. The first production helmet blank slides into position on the press bed. The operator, a man named Joseph Mazur, who had worked for McCord for 16 years, checks the blank holder one final time. He's made thousands of test runs over the past month, learning how to read the steel, understanding the tiny differences in how the metal sounds when it's flowing correctly versus when it's about to tear. McCord himself stands beside the press, along with representatives from the Army Ordnance Department and several skeptical military engineers who have come to witness either success or failure. Mazur engages the press. The flywheel's momentum drives the ram downward with controlled precision. 700 tons of force flows through the punch into the steel blank. The metal resists for a fraction of a second, then begins to yield. The blank flows into the die cavity, following the carefully designed contours that guide its transformation. Steel that was flat moments before curves and stretches, its thickness remaining uniform as it assumes the distinctive shape that will become iconic across the next 4 decades. The press completes its stroke and returns to top position. Total elapsed time, 4 seconds. The helmet shell emerges from the die. 7 inches deep. Smooth walls. No cracks, no wrinkles, no tears. The Army inspectors measure it carefully, checking dimensions against the specifications. Wall thickness, within tolerance. Depth, exact. The rim area, perfectly formed for the reinforcing band that will be welded later. One of the military engineers, a major who had told McCord 3 months earlier that single-stroke deep drawing was metallurgically impossible, runs his fingers along the helmet's interior surface and says nothing. McCord looks at the production schedule pinned to the wall above the press. 323,510 helmets. First delivery date, December 1st, 1941. The press can cycle every 12 seconds when running at full speed, accounting for blank loading and part removal. That's 300 helmets per hour if everything works perfectly. 2,400 per 8-hour shift, 7,200 per day running 3 shifts, 43,200 per 6-day week. The mathematics suddenly look different. Not impossible, merely difficult. McCord authorizes the purchase of 2 more press lines. The race against time has begun, though no one in that Detroit factory on that June afternoon knows just how urgent the race will become. 6 months from now, Japanese aircraft will turn Pearl Harbor into a burning graveyard, and the United States will discover that the ability to manufacture protective equipment faster than enemies can kill American soldiers will determine who survives the coming war. The deep draw process that McCord had perfected represented a quiet revolution in metalworking. For over a century, military helmets had been formed through multiple operations. The French Adrian helmet of World War I required 4 separate stamping stages plus hand finishing. The British Brodie needed 3 stampings and extensive trimming. The German-style helm went through similar multi-stage press forming. Each additional operation meant more time, more equipment, more skilled workers, and more opportunities for defects. McCord's single-stroke process eliminated all of that. A flat disc entered the press. 4 seconds later, a nearly complete helmet shell emerged. The productivity implications were staggering. A traditional multi-stage helmet line might produce 1,500 helmets per day from multiple presses, furnaces, and trimming stations, requiring dozens of workers. McCord's line could produce 7,000 helmets per day from a single press with 3 operators per shift. But the real genius lay in what engineers call process consistency. Every helmet pressed from the same die, using the same steel grade, was virtually identical. Wall thickness varied by less than 5/1000ths of an inch. Depth was consistent to within 1/8 of an inch. The helmets nested perfectly during transport, stacking cleanly without jamming. Most importantly, the steel's grain structure remained uniform throughout the deep draw, creating consistent ballistic resistance. A helmet pressed in July would provide the same protection as one pressed in December. The steel itself presented its own challenges. Hadfield manganese steel, developed by British metallurgist Robert Hadfield in 1882, possessed remarkable properties. It was tough without being brittle, hard enough to resist penetration but ductile enough to absorb impact energy. Under shock loading, such as from shrapnel impact, the steel's grain structure would transform, becoming even harder at the point of impact while the surrounding material remained flexible. It was the ideal helmet material, if you could work with it. The problem was that Hadfield's steel was notoriously difficult to form. Its work-hardening properties, the very characteristic that made it excellent for armor, meant it fought back during stamping. Apply too much force too quickly, and the steel would crack. Apply too little, and it would spring back, refusing to hold the pressed shape. The deep draw process required finding the exact window where the steel was ductile enough to flow, but hard enough to maintain shape. Carnegie Illinois Steel Corporation and Sharon Steel Corporation, the 2 suppliers providing blanks to McCord, had to maintain extraordinarily tight control over their production. Each heat of steel, a single furnace batch weighing several tons, was assigned a unique identification number. When that steel was rolled into sheets and blanked into discs for helmet production, each batch received its own lift number within the heat. The combination of heat and lift numbers stamped into every finished helmet allowed quality control inspectors to trace any defect back to its source in the steel mill. This traceability system, considered revolutionary in 1941, meant that if a helmet cracked during testing, inspectors could determine whether the failure was due to pressing, problems at McCord, or steel quality issues at the mill. More importantly, if a heat of steel showed problems, every helmet pressed from that batch could be identified and inspected before shipment. The system prevented defective helmets from reaching soldiers in combat. By September 1941, McCord's production line was running at full capacity. The presses operated 24 hours a day, 6 days a week. Sunday was reserved for maintenance, when toolmakers would inspect the dies for wear, replace worn components, and ensure everything was within tolerance for Monday morning's restart. Each die set could press approximately 50,000 helmets before requiring major refurbishment. The company maintained 6 complete die sets in rotation, with 2 sets being refurbished while 4 were in active production. The factory floor had transformed into something resembling an industrial ballet. Raw steel blanks arrived by railcar from Pittsburgh, unloaded onto roller, conveyors that fed the press lines. Operators placed blanks into the press fixtures with movements refined through thousands of repetitions. The presses cycled with rhythmic precision, their flywheel momentum converting into controlled forming force. Pressed helmet shells emerged on the opposite side, where inspectors examined each one before sending it to the next operation. After pressing, the helmets required additional work. A second press trimmed the excess metal from the rim area, creating the clean edge that would accept the reinforcing band. The rim itself, formed from steel rod in yet another massive press, was welded to the helmet shell using electric resistance welding. The weld had to be continuous and strong, capable of handling the stress of combat use without separation. Quality control inspectors X-rayed random samples from each production run to verify weld integrity. Paint application came next. The helmets traveled through a spray booth, where workers applied olive, drab shade 319 paint mixed with finely ground cork. The cork created a non-reflective, textured surface that wouldn't shine under sunlight or starlight, helping soldiers avoid detection. The texture also provided better grip when handling the helmet with wet hands. Each helmet received the paint coating while still warm from the welding operation, allowing the paint to flow into every surface detail and cure more quickly. The heat stamp, that cryptic combination of numbers and letters that collectors would scrutinize decades later, was applied to the front interior of each helmet shell before painting. A pneumatic press forced hardened steel stamps into the warm metal, deforming it permanently to record the lot and lift information. The stamps had to be deep enough to survive years of wear, but shallow enough not to weaken the helmet's structure. The marking system was so effective that historians can still determine the approximate production date of helmets recovered from battlefields across the world. By October 1941, McCord's daily production had reached 7,500 helmet shells. The company employed over 400 workers directly on helmet production, with hundreds more in supporting roles. Tool and die makers worked around the clock, maintaining and repairing the massive dies. Quality control inspectors tested sample helmets to destruction, shooting them with regulation military ammunition to verify ballistic performance. The helmets that passed inspection were painted, packed, and shipped to army depots where they awaited assignment to training camps across the United States. The Army's original order for 323,510 helmets represented just the beginning. Military planners were calculating requirements for a force that didn't yet exist, an army of millions that would need equipping if war came. The War Department's tentative estimate suggested America would need 4 million helmets for its expanding Army and Marine Corps. The Navy would need hundreds of thousands more for its growing fleet. And there would be losses, the grim but necessary, accounting for helmets damaged in combat, lost in training accidents, or simply worn out through hard use. McCord received authorization in November 1941 to expand production capacity. The company purchased additional press lines and began construction of an expansion to its existing factory building. More critically, the company started training new workers. The press operators needed weeks to develop the sensitivity required to hear when the steel was forming correctly. Die maintenance required highly skilled toolmakers who understood metallurgy and precision grinding. Even the inspectors needed extensive training to identify the subtle signs of impending die failure or steel quality problems. December 7, 1941. The Japanese attack on Pearl Harbor transforms America's military preparedness from theoretical planning into desperate necessity. Within hours of the attack, the War Department begins revising its equipment requirements upward. 4 million helmets won't be enough. Neither will 6 million. Initial estimates for a two-ocean war requiring simultaneous operations in Europe and the Pacific suggest America will need between 15 and 20 million helmets over the next 4 years. Frank McCord receives a phone call from the Army Ordnance Department at 6:15 in the morning on December 8, Washington time. Detroit is still dark, and McCord is in his office anyway, having come in at 4:30 as he does every morning. The voice on the phone is flat with exhaustion and stress. The United States is at war. How many helmets can you deliver per month? McCord looks at his production schedules, does rapid calculations in his head. 400,000 per month if we run full capacity, he says. Can you do more? The voice asks. McCord thinks, about the expansion already underway, the additional presses on order, the training programs, preparing new workers. "Give me 4 months to complete the expansion," he replies. "By April we can do 600,000 per month. Will that be sufficient?" There's a pause on the line. 600,000 per month will be adequate if you can sustain that rate for the duration, the voice finally says. "One more thing. We're bringing in a second contractor to supplement your production. Schluter Manufacturing in St. Louis. They'll need your technical assistance to set up their deep draw lines. Can you provide engineering support?" McCord agrees without hesitation. The conversation ends. He sits at his desk for several minutes, considering what he has just promised. 7,200,000 helmets per year from his plant alone. More than 20,000 helmets for every working day of the year. The quiet revolution in metalworking that began in his office 15 months earlier has just become America's shield in a global war. Whether McCord's presses can deliver on that promise will help determine whether American soldiers fight with protection or without it, whether they come home or don't, whether the United States possesses the industrial capacity to wage war on 2 fronts simultaneously. Everything depends on whether a company that made automobile radiators can transform cold steel into life-saving equipment faster than America's enemies can produce soldiers to fight. January 19th, 1942. Schluter Manufacturing Company, St. Louis, Missouri. A team of engineers from McCord Radiator stand in a cavernous factory building that until 3 weeks ago produced stamped metal components for washing machines and kitchen appliances. Now they're installing the first of 4 massive deep-draw presses that will transform this facility into America's second helmet production center. The race to equip America's military has forced industrial conversion on a scale never before attempted. Edward Schluter, the company's founder, watches as a 10-ton press bed is lowered onto its foundation. His plant had received the War Department contract on Christmas Eve, 1941. Expected delivery of first production helmets, March 1942. Schluter's engineers have 11 weeks to master a manufacturing process that took McCord over a year to perfect. The margin for error is 0. American soldiers are already in combat in the Philippines, fighting with equipment stockpiled before the war. Those supplies won't last past spring. McCord's engineers bring more than blueprints. They bring experience. The thousands of small lessons learned through trial and error on the Detroit production lines. How to recognize when a die is beginning to fail by the sound the press makes. The correct temperature for the steel blanks to achieve optimal forming. The precise pressure needed for the blank holder to prevent wrinkles, without crushing the metal. The maintenance intervals that prevent catastrophic tool failures. This knowledge transfer, engineer to engineer, represents industrial cooperation driven by wartime necessity. The first Schluter press cycles on February 8, 1942. The helmet shell that emerges looks identical to those from Detroit, which is exactly the point. Interchangeability, the concept that any helmet liner from any manufacturer should fit any shell from any producer, drives the Army's standardization efforts. Soldiers cannot waste time in combat determining whether components match. Everything must work with everything else. First time, every time. Schluter's production team spends the next 3 weeks refining their process until they achieve Detroit's quality standards. By March 1942, Schluter's 4 press lines are producing 3,200 helmets per day. It's half McCord's output, but it represents a critical expansion of America's manufacturing capacity. More importantly, the successful technology transfer proves that McCord's deep draw process can be replicated. The knowledge isn't locked in one engineer's mind or dependent on irreplaceable craftsmen. It's a systematic industrial process that can be taught, learned, and scaled. This reproducibility will prove as important as the original innovation. The 2 plants develop a subtle form of industrial competition. Schluter stamps an uppercase S beneath the heat stamp on every helmet they produce, distinguishing their output from McCord's. The marking system allows quality control inspectors to track performance by manufacturer. Initially, Schluter's rejection rate runs slightly higher than McCord's. Within 6 months, the St. Louis plant matches Detroit's quality metrics. By late 1942, some Army inspectors claim Schluter helmets are slightly superior in wall thickness consistency, though the difference exists only in statistical measurements, too small to matter in combat. What does matter is the combined output. Two plants producing over 20,000 helmets per day, 500,000 per month, 6 million per year. These numbers seem staggering until measured against the scale of America's mobilization. The War Department projects it will put 16 million men and women into uniform before victory. Every one of them will need a helmet. Many will need 2 or 3 over the course of the war, replacing helmets damaged in training accidents, lost during amphibious landings, or destroyed by enemy fire that would have killed the wearer without that protection. The production statistics paint a picture of industrial acceleration that defies easy comprehension. In 1941, before Pearl Harbor, McCord produced 323,510 helmets. In 1942, with both plants running full capacity, total production reaches 5 million. 1943 sees production peak at 7,648,880 helmets. That's 20,959 helmets per day, every single day, for an entire year. More helmets than the entire United States Army contained soldiers at the start of 1941. Behind these numbers stand human beings. Women who had never worked outside their homes before the war now operate presses generating 700 tons of force. Their hands learn to place steel blanks with millimeter precision. Their eyes develop the ability to spot imperfections that quality control instruments sometimes miss. A surface scratch, invisible to casual inspection, becomes obvious to experienced press operators who understand that minor defects can propagate into catastrophic failures under combat stress. The work is hard, sometimes dangerous, and always demanding. Press operators stand for 8-hour shifts in factories where summer heat makes the air shimmer above the massive machines. The noise level from stamping operations requires workers to communicate through hand signals and experience rather than verbal instructions. Safety protocols demand constant attention because a moment's inattention around a press cycling with 700 tons of force can result in tragedy. Yet the work continues, day after day, driven by photographs in newspapers and letters from brothers, sons, husbands serving overseas. Die maintenance emerges as the critical limiting factor in production sustainability. Each die set can press approximately 50,000 helmets before the forming surfaces begin to show measurable wear. At peak production, McCord's 4 press lines are completing 50,000 helmets every 6 days. The dies require constant monitoring, measurement, and refurbishment. Tool and die makers work in climate-controlled rooms where temperature and humidity are carefully regulated. They use precision grinding machines and hand lapping techniques to restore die surfaces to original specifications. The dies themselves represent an achievement in metallurgy and toolmaking. Each complete die set weighs several tons and consists of multiple components that must work in perfect harmony. The punch, which forces the steel blank into the die cavity, is made from tool steel heat-treated to withstand repeated high-stress loading without deforming. The die cavity must be equally hard but also resistant to the abrasive wear caused by steel flowing across its surface at high pressure. The blank holder, which restrains the edge of the steel disc during forming, requires different properties still, providing controlled pressure without crushing. Creating a single die set requires approximately 800 hours of skilled labor from master toolmakers. The components start as rough castings that must be machined to within thousandths of an inch of final dimensions. Heat treatment transforms the steel's microstructure, achieving the precise balance of hardness and toughness needed for production use. Final grinding and polishing create the smooth, precise surfaces that will impart their shape to every helmet pressed from that die. Each die set costs approximately $18,000, enough to buy 3 new houses in Detroit in 1942. The economics of helmet production reveal why single-stroke deep drawing proved essential to meeting wartime demand. Traditional multi-stage forming would require approximately 3 times as much equipment and labor to achieve equivalent output. The capital investment for presses, dies, furnaces, and ancillary equipment would exceed McCord and Schluter's combined expenditure by a factor of 4 or 5. More critically, the skilled labor requirement would be unsustainable. America simply didn't have enough experienced metal workers to operate traditional multi-stage helmet production at the scale required. McCord's innovation allowed semi-skilled workers, trained for weeks rather than years, to produce high-quality helmets at extraordinary volume. The simplified process meant quality control could focus on a smaller number of critical parameters. Press operators monitored blank positioning, cycle timing, and oil supply to the dies. Inspectors checked dimensions, wall thickness, and surface quality. The process's inherent consistency meant that once a press was producing good helmets, it would continue producing good helmets until something broke or wore out. Continuous improvement came from refining the things that could vary: steel quality, die maintenance intervals, operator training. By summer 1942, helmet production had become a model for other military equipment manufacturing programs. War Department industrial efficiency experts studied the McCord and Schluter operations, attempting to extract lessons applicable to artillery shell production, small arms manufacture, and aircraft component fabrication. The key, insights seemed simple in retrospect, but had required McCord's initial breakthrough to make obvious. Design manufacturing processes for scale from the beginning. Simplify wherever possible. Train workers systematically rather than relying on traditional craft knowledge. Monitor quality continuously rather than inspecting finished products. The steel supply chain supporting helmet production represented its own logistical achievement. Carnegie, Illinois and Sharon Steel together produced over 60,000 tons of Hadfield manganese steel specifically for helmet manufacture during the war. That steel began as iron ore mined in Minnesota's Mesabi Range, transported by ore carrier across the Great Lakes to blast furnaces in Pittsburgh and Sharon. The steel mills added precise quantities of manganese, carbon, and other alloying elements to achieve the specified properties. Rolling mills transformed ingots into sheets of exact thickness. Blanking presses cut those sheets into discs 12 inches in diameter. Every step in this process required careful coordination. The steel mills had to maintain production schedules that kept pace with pressing operations in Detroit and St. Louis. Any disruption in steel supply would force press lines to shut down, wasting capacity that could never be recovered. Conversely, producing steel faster than the presses could consume it created inventory problems, tying up capital and warehouse space needed for other war materials. The logistics officers who managed this supply chain worked with tolerances measured in days rather than weeks, constantly adjusting production rates and shipment schedules to maintain flow without building excessive inventory. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The rail system connecting these operations became a critical vulnerability and a testament to American logistics. Loaded railroad cars left Pittsburgh multiple times per week, carrying steel blanks to Detroit and St. Louis. Empty cars returned for refilling. Finished helmets traveled by rail from the pressing plants to army depots in over 24 locations across the United States. This continuous flow of materials required coordination between multiple railroad companies, all while the rail system simultaneously supported countless other war production programs. A single derailment or equipment failure could cascade through the entire production system, delaying helmet deliveries to training camps where new soldiers needed equipment for deployment overseas. The human cost of this production miracle remained largely invisible to the soldiers who wore the helmets. Worker fatigue became a growing concern as the war continued year after year. Factory managers experimented with shift schedules, attempting to maintain production while preventing the accidents that came from exhaustion. Some plants switched to 12-hour shifts with rotating schedules. Others maintained 8-hour shifts but increased the frequency of short breaks. Medical officers monitored injury rates and recommended changes when specific operations showed elevated accident frequencies. The gender composition of the workforce changed dramatically as the war progressed. In June 1941, when McCord began helmet production, virtually all press operators and die maintenance workers were men. By July 1943, women comprised over 60% of McCord's helmet production workers. They operated presses, inspected finished helmets, maintained equipment, and performed quality control testing. Many proved as skilled as the men they replaced, and some supervisors quietly noted that women's generally smaller hands provided advantages when performing detailed maintenance work on complex dies. Racial integration proceeded more slowly and unevenly. Both McCord and Schluter employed black workers in significant numbers, but segregation patterns from civilian life persisted inside the factories. Separate locker rooms and cafeterias remained standard through most of the war. Black workers generally received lower-paying positions regardless of skill level. Yet the sheer demand for labor gradually forced changes. By 1944, some of McCord's most experienced press operators were black workers who had joined the company early in the war and developed expertise that made them invaluable. The Army's needs cared nothing for peacetime prejudices. The technical challenges of sustained high-volume production manifested in unexpected ways. Die wear patterns proved more complex than initial engineering calculations suggested. The center of the die cavity, where steel flow rates were highest, showed accelerated wear compared to edge areas. This differential wear gradually changed the helmet's internal contours, creating subtle variations in wall thickness. Quality control. Inspectors developed increasingly sophisticated measurement protocols to detect these changes before they exceeded tolerance limits. By late 1942, both plants had implemented statistical process control techniques that analyzed measurement data from sample helmets to predict when dies needed refurbishment. Steel quality variations presented another ongoing challenge. Even with careful controls at the steel mills, minor differences in chemical composition and grain structure affected how the metal behaved during deep drawing. Some batches flowed more easily, requiring less forming force. Others resisted deformation and required maximum press capacity. A particularly hard batch could accelerate die wear significantly. A batch that was too soft might not maintain proper shape after pressing, springing back slightly and requiring additional sizing operations. The pressing operators learned to recognize these differences and adjust their techniques accordingly. Though major, variations still required engineering intervention. The war's progression created new requirements that complicated production planning. The standard M1 helmet served infantry forces effectively, but specialized units needed modifications. Paratroopers required different chinstrap attachments to prevent helmets from being torn away during parachute opening shock. These M2 helmets used D-shaped bales instead of the standard rectangular loops. The modification seemed minor, but it required different welding fixtures and created a separate production stream within the main manufacturing process. By 1943, McCord was producing multiple helmet variants simultaneously, each requiring careful tracking to ensure the right helmets reached the right units. Quality control testing evolved from simple dimensional checks to comprehensive ballistic evaluation. Army inspectors regularly pulled sample helmets from production for firing tests. They mounted the helmets on ballistic gel, forms approximating human heads, and shot them with typical shrapnel loads and small arms ammunition at various ranges and angles. The helmets were designed to stop typical shrapnel fragments and glancing pistol rounds, not direct rifle fire, but the testing revealed how manufacturing variations affected performance. A helmet with slightly thinner walls in one area might fail a test that a properly formed helmet would pass. These failures triggered investigations into the production process that created that helmet, leading to adjustments in pressing parameters or die maintenance schedules. The statistics from this testing painted a picture of remarkable consistency. Throughout the war, production helmet shells maintained rejection rates below 2% for ballistic performance failures. The vast majority of rejects failed for cosmetic reasons: paint defects, minor dings from handling, scratches that didn't affect structural integrity but looked unprofessional. The helmets that passed inspection consistently demonstrated the protection they were designed to provide. This reliability came from the systematic approach to manufacturing that McCord's innovation had enabled. By 1944, with Allied victory in Europe appearing inevitable, helmet production began to decrease from its 1943 peak. The War Department had accumulated substantial inventory in depots worldwide. Replacement demand remained steady as helmets were damaged or lost in combat, but the massive production required to initially equip millions of soldiers was complete. McCord and Schluter produced 5,700,000 helmets in 1944, still an enormous number, but a marked decrease from the previous year's output. The skilled workers who had learned precision metalworking during wartime production now faced uncertain futures. Some would remain in manufacturing after the war, applying their expertise to civilian products. Others would leave industrial work entirely, having joined the factories only from patriotic duty during the emergency. The factories themselves would retool for peacetime markets. McCord would return to radiators and automotive components. Schluter would resume appliance manufacturing. But the lessons learned during helmet production would persist, informing American manufacturing practices for decades. The helmets themselves would see service far beyond World War II. The M1 design proved so successful that it remained in American military use until the mid-1980s, when the PASGT helmet finally replaced it. Over those 4 decades, the original manufacturing techniques pioneered by McCord continued in use, with only minor refinements. The deep draw process remained the standard method for forming helmet shells. The quality control approaches developed during wartime production evolved into more sophisticated statistical process control methods. But the fundamental principles remained unchanged. Foreign militaries copied the M1 design extensively. France, Belgium, Austria, and numerous other nations adopted helmets directly based on American specifications. Some purchased surplus American helmets. Others manufactured their own copies using technical information shared through military assistance programs. The distinctive silhouette of the M1 helmet became a symbol of Western military forces during the Cold War, instantly recognizable in news photographs from Korea, Vietnam, and countless smaller conflicts. The total production during World War II exceeded 22 million helmet shells. McCord produced approximately 20 million of those. Schluter manufactured 2 million. A third contractor, Parish Redding in Pennsylvania, produced a small number in 1945 before war's end. These numbers represent more than industrial statistics. Each helmet potentially saved a life. Each one represented American industrial capacity translated into protection, for soldiers fighting thousands of miles from home. The mathematics of saved lives resists precise calculation. How many soldiers survived wounds that would have been fatal without helmet protection? Medical records from the war document thousands of cases where shrapnel struck helmets, denting or penetrating the steel, but dispersing enough energy that the soldier survived with minor injuries or no injuries at all. Photographs from the war show helmets with dramatic damage. Shell fragments embedded in the steel, bullet impact marks, blast damage from nearby explosions. In each case, the helmet absorbed force that would otherwise have struck an unprotected human head. Combat veterans developed a complicated relationship with their helmets. The M1 was heavy, uncomfortable during long marches, and provided only partial head protection. It didn't stop rifle bullets. It couldn't prevent concussive injuries from nearby artillery explosions. Soldiers in the Pacific Theater complained about the heat build-up during tropical operations. Yet when enemy fire came, veterans instinctively trusted the steel pot. They knew it had limitations, but they also knew it was vastly better than nothing. Photographs from every theater of the war show soldiers wearing their helmets even in supposedly safe rear areas, the automatic reflex of men who had learned that safety was always relative in a combat zone. The final helmets rolled off the production lines in August 1945, immediately after Japan's surrender. Over 4 years and 2 months, 2 factory plants in Detroit and St. Louis had produced enough helmets to equip every soldier, sailor, and marine in America's 16 million strong military force, plus substantial surplus for training, testing, and replacement. The accomplishment represented American industrial capacity at its peak, the ability to identify a need, develop a solution, and scale production to meet demand levels that seemed impossible at the program's start. Frank McCord, whose late-night engineering calculations in September 1941 had enabled this achievement, remained with the company until his retirement in 1963. He never spoke extensively about his role in helmet development, viewing it as simply part of his job as a production engineer. The patents covering the deep draw process listed multiple inventors, as most industrial innovations do. McCord's name appeared alongside his colleagues, sharing credit for work that was genuinely collaborative, even as his initial insight had made everything else possible. The steel pot, as soldiers called it, outlived most of the men who designed and built it. Helmets pressed in 1942 were still in use in Vietnam 2 decades later, the steel showing decades of wear but still fundamentally sound. Some of those helmets eventually found their way into museums and private collections, where they remain today as physical artifacts of American industrial mobilization. The heat stamps inside each helmet, those combinations of numbers and letters that once tracked quality control across the steel supply chain, now allow historians and collectors to determine when and where each helmet was manufactured. The deeper story that those helmets represent extends beyond military history into the realm of industrial capability. McCord's innovation, the single-stroke deep draw process that made high-volume helmet production possible, was fundamentally an engineering solution to a manufacturing problem. Traditional metalworking wisdom said deep drawing at that scale couldn't be done. McCord and his team refused to accept that limitation. They applied systematic engineering thinking to understand why the limitations existed, then designed around those constraints. This approach, solving impossible problems through careful analysis and creative engineering, characterized much of American industrial achievement during World War II. The nation didn't win the war simply through superior numbers or resources, though both mattered. America won in part because its industries could rapidly develop and deploy manufacturing processes that didn't exist before the war began. The proximity fuse, the Liberty ship, the B-29 bomber, and countless other war-winning technologies emerged from this same pattern. Identify the problem, engineer a solution, scale production rapidly. The helmet production program demonstrated all of these principles, operating at high efficiency. A civilian company with no military production experience transformed its capabilities to meet wartime needs. Engineers with expertise in automobile radiators applied their knowledge to helmet manufacture. Workers with no metalworking experience learned precision production techniques and sustained quality levels that impressed military inspectors. The entire system functioned because people at every level understood that their work mattered, that the steel passing through their hands would protect American lives in combat. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.